present our results. So I have decided to divide the talk in three parts. So the first one is going to be non-negative polynomials and sum of squares representations, which is going to be kind of a dual view of what Tony presented this morning about these hierarchies. And then I'm going to apply this methodology to the problem at hand, which is to characterize many-body correlations. So first, a bit of history, right? Motivation about why non-negative polynomials are important, or should one care about this, is that, well, you can apply them to all these kind of situations, right? And the last one is the one that I'm going to talk about today here, but if you need to help for writing the introduction to your paper, I think that this can be useful. So also a bit of history, non-negative polynomials. So this goes back to David Hilbert that, well, in very poetic terms, he proposed that in 1900, a list of 23 open problems that were very important at that time. So for instance, the first one is a continuum hypothesis, right? The 8th is a Riemann hypothesis and something else because it was too easy, right? Only the Riemann hypothesis. And the 17th is the one that is related to non-negative polynomials, right? So given a multivariate non-negative polynomial, does it admit a sum of squares representation? This is very related to what I'm going to present here, right? And well, Hilbert's 17th problem. So you can formalize it in this way. So we have a polynomial of many variables, right? That is positive. Can I express it as a sum of squares of other polynomials that are also multivariate? So you see that the is trivial because if I have a sum of squares, this automatically is positive, right? But is it equivalent always, or in which situations, right? And also, I think kind of valid is how powerful is this representation. What I will be using actually for our results is if one can extend it just to a subset of Rn. So a semi-algebraic set, which means a set of zeros of polynomials, and a set where some other polynomials are non-negative. So let's look at what instances are true to situate ourselves, right? So if n is the number of variables and 2d is the degree of the polynomial, and now I'm considering all the domain like Rn. Of course, just even degrees, right? Then it was proven that if the polynomial is univariate, then it's equivalent to having a sum of squares. And if you have but the degree is 2, then you see that you can express it in this way. So if this matrix Q is positive semi-definite, then you can find composition, and then you automatically have the sum of squares. And well, Hilbert also proved in a non-constructive way that this case here in dark green is also true, and the other cases are false. And well, the thing is that there are textbook examples to that, and the textbook counterexample that was found much later, which is the Motzkin polynomial, which follows from this inequality. So the geometric mean of some numbers is always bounded by the arithmetic mean. So this gives you this polynomial, which is non-negative. Here you have the proof of this. But this does not admit a sum of squares representation. So this sometimes it fails. Right, and what I think is surprising is that not even if you add an arbitrarily large constant to this polynomial, this becomes a sum of squares. Right, but actually, well, it's a bit puzzling that now if you multiply this by another positive polynomial, now the product admits a sum of squares decomposition. Right, and this is kind of the tool that Artin used later to solve the problem actually. So that every multivariate non-negative polynomial over the reals can be written as a sum of squares of not polynomials but rational functions, right? And then of course it's hard to decide whether now if I give you a polynomial if it's non-negative, right? But at least you have this kind of representation. So this non-negative polynomials, they appear in many instances, as I have shown in my first slide. So is there a tractable approach to this question, right? And the tractable approach is to use semi-definite programs because one can solve them efficiently. And well, just let me mention that in the non-commutative case, that it's known that the sum of squares is equivalent to positivity, right? And this is Helfson's theorem. So here, positivity means that when you evaluate a polynomial on any Hermitian operator, right, it's positive even only if it's a sum of squares. So let me illustrate that with an example. So if you consider this polynomial, right, then this is a sum of squares over the reals. But if instead of putting real entries, I put semi-definite, I put Hermitian operators. For instance, these 2 by 2 matrices, right? This may fail. So in this case, in the non-commutative case, you would have equivalence. Okay. So sum of squares are syntactic certificates, right? So the only logic that I'm using here is that well, I have some kind of that squares are non-negative, right? So I add them, and then I have the proof of positivity, right? But it doesn't really care about what a polynomial or its variables are, right? So you can generalize it in many ways. Right, and for instance, if you want to prove the Cauchy-Schwarz inequality, right, it follows trivially from writing it in this form, just as an example. Okay, so let me go to the sum of squares representations, right, and then, well, for this we would use semi-definite programming. So it's very important in semi-definite programming what is called the primal dual formulation. So in canonical form, you would write a semi-definite program in this way, right? So this is the scalar product between matrices of the trace of C times X, such that you have some linear constraints, and X is a positive semi-definite matrix, right? And you would associate a dual problem. And the idea is that you would have a cone of semi-definite matrices. You intersect it with a hyperplane that is given by these constraints here, right? And then you optimize some objective function over this, right? And then let's say that these are efficiently solvable, right? When you do your PhD and you try to solve some of them, you see that maybe they are not as efficiently solvable as you would like to, but in principle, well, in the notation, they are. Right, and then now deciding if a polynomial that means a sum of squares representation, it's simply an SDP in disguise, right? So I mean, and if we are over the reals, right? I mean Rn, right? It's an easy one because you can bound the degree of these polynomials here, right? And then you just okay. I think that maybe if we take an example, it's very easy to see, right? So I consider this polynomial. I want to write it as a sum of squares, right? So I would write this way, right? And this Q matrix, I will make it positive semi-definite, right? So I just solve these equations, and I see that, well, there are going to be some dependencies, right? And this is just a typical instance of a semi-definite program. So in this case, this would be a solution. You factorize it in this form, and this will give you the of the sum of squares. I think that more or less everyone here is a bit familiar with this. It is where I'm going a bit faster. So now let's consider a bit more interesting case. So let's say that I'm interested in the set of points that satisfy this relations is equal to 0, right? So I'm just interested in this parabola, the blue points. So I want to prove that this polynomial, which is linear, right? So this we can see that's a linear inequality, which is the orange curve. Right, so this is just a toy example, but I think it's just one of the ideas that I'm going to use later. So if I want to prove that this is true on the blue points, right, then, well, simply I'm using the fact that y is equal to x squared, right? So I can write it this form. So it means that I have now expressed my polynomial as a sum of squares, only one square, right? But this means that this is positive. It's non-negative on every point that is a 0 of f. Right, so I have proven this inequality here, right? So in mathematical terms, one would say that one considers the ideal generated by a set of polynomials, right? And then this is the methodology at hand, right? And sum of squares modulo ideals are quite powerful, right? So it means that now I can represent my y as any of these polynomials here. So f are polynomials that are going to be 0 on the points of interest. I can multiply this by any arbitrary polynomial, right? And then this whole expression for some choice of g's admits a sum of square representation, then I have my proof, which is completed, right? Yeah. But now we have a problem, right? Which is that the degree of the sum of squares can be unbounded because, so let's take another example, like let's say the zeros of this function, which is kind of this manifold here written in, plotted in blue, right? So this means that I have a simplification rule. Every time I would have an x to the 4, I can substitute it by this, right? So this is where of the problem comes, because here I only have one polynomial, but if I have many, right, then I would have to find a way to make the substitution in an efficient way. So we have to solve some Gröbner basis, right? And then, well, what I would like to solve, this Q matrix is going to look something like that, right? So I would have x and y, my variables, but then I would have kind of powers of x, powers of y, cross terms, and so on. I would realize this using these w's, which are kind of the unknowns in my SDP, and well, I would have some dependencies that are going to be given simplification rule, right? So we'll have, in this case, a matrix. This would be second order because I would take up to terms of x to the 4, and so this would be the way to try to find sum of squares modulo f. And one can also twist a bit more the method and add inequality constraints. So let's say that on top of that, I'm interested on only on the part of the manifold that is for positive x, right? So something like that. And then I have my moment matrix, which is given by the polynomial defining the ideal. And on top of that, I can make a shifted moment matrix that is presenting this constraint, right? So here, if I take this submatrix, which would be and then I multiply it by x, I would get another moment matrix here that will be shifted, and making both of them positive semi-definite, I would take both conditions into consideration. So in general, to describe these convex hulls of semi-algebraic sets, so sets that look like this, I want to find the convex hull of S. I will be looking at inequalities, linear inequalities of this form, right? So sigma 0, so the sigmas are sum of squares modulo I, and g's are just the polynomials that are given to be positive. So you see that this whole expression is always non-negative on S, right? So then you see that this naturally gives you to a hierarchy, because if you increase the degree of these sigmas that you allow here, right, you would increase the degree of your semi-definite program, and then this would give you this can only give you more representability power, right? So you can only get better and better inequalities. So here the black curve would be your manifold, right? And then the gray area would be kind of the level 1 of the hierarchy, and then the light gray area would be the level 2, which approximates a bit better the convex hull of your manifold. Okay, so these are the preliminaries of that I wanted to kind of give a general view of the method. So here what we're interested in is to characterize many-body correlations of, so you have a many-body system and you would perform measurements on it, and you would like to know if the statistics that are produced are local or non-local, right? So we are in the Bell-type experiment where you have Alice and Bob, right? Each of them have their laboratory, right? But maybe you cannot trust Alice or Bob for different reasons, right? So you prefer not to also make any assumption on what is going on inside of their laboratories, right? And then, well, you have the inputs, which are the measurements that they perform, and then in the end of the day, you estimate these probabilities, right? So now, instead of having only Alice and Bob, I would have a many-body system. So you have a multipartite probability distribution, and I would like to say if this is local or it's non-local. So, well, if we look a bit on the complexity of the problem, well, this has already been said. Also, so sorry for repeating a bit, right? But well, finding all the Bell inequalities is the equivalent to finding the convex hull problem, right? So we have a local polytope that we know how to generate the vertices. I would not say in an efficient way because there are exponentially many of them, especially if the number of parties is large, right? So if you have n parties with n m inputs and d outcomes, right, then you see that the dimension of the polytope is more or less this number, which grows exponentially with n, the number of parties. The number of vertices, it's also terrible. And now you look at a bit what is the algorithm that you can find to solve the, so given the vertices, generate all the inequalities, and you see that it has a doubly exponential complexity on with this, right? So this means that if you use a computer, so the test is done like 5 years ago, so now the numbers are a bit better, right, with the increase of technology. But I mean, 5 years ago, this was order of milliseconds, right? And then if you put like 3 parties, you would have 5 minutes, and just by extracting, you would see that for parties it would take 10 to the 67 years, right? A bit less because the technology is better, as I said, right? But here we are interested in a many-body regime, right? So it's something that like, I don't know, 10 to the 4 parties, right? So it's something that is independent, I would say, on the time scale that you use, actually, right? Doesn't matter if these are nanoseconds or centuries. So it's a very hard problem, and you have to simplify it somehow, right? And then, the way to reduce the mathematical complexity is not to find all the Bell inequalities, but find some of them of a specific form, right? So if we say that in the case of 2 inputs, 2 outputs, we have this polytope with the exponential number of vertices and dimension, right? We can say we are going to focus on just Bell inequalities with 2-body correlators. So this simplifies the dimension of your polytope, because now you are not considering as many multipartite correlators, just the 2-body ones, but you still have the same number of vertices. So you can say, okay, I'm now going to apply an action of a symmetry group on this, right? So cyclic or symmetric group, and then this will reduce the dimension of your polytope to a constant, but still have many vertices. And well, then you can also make some tricks, as we do in these papers, to further simplify this, right? So now we have polynomial number of vertices, which is something that is tractable. So some applications of our method is what is in this paper that we wrote with Matteo, as a PhD student from the group of Troitlind in Basel. And here we said, okay, instead of trying to solve the polytope, which is clearly not practical, we're going to think of the problem in the following way, right? So you go to the laboratory and you collect some statistics, which are this star point here, right? And then you want to find the Bell inequality that they violate, if they violate a Bell inequality, right? Not start checking all the list of Bell inequalities, which may be very, very, very large, and you don't, well, depending on the polytope that you are dealing with, you may never finish, right? But to find some kind of test that would give you the Bell inequality that you are violating, and a proof that this is a valid Bell inequality, actually, right? So we want to certify Bell correlations from experiments, and we also want to find a new method to generate Bell inequalities that are actually the relevant ones. Right, so here we are going to consider Bell inequalities of this form. So these H's are just k-body symmetric correlators. So you see that I have kind of a correlator that I sum over all the possible permutations of parties. Right, so these numbers are independent of the number of parties, actually, right? Because this gets washed out here, right? And then you have some alphas, which are the coefficients of your Bell inequality, and the classical bound. Okay, you sum this, and you form your typical Bell inequality. So here the dimension of the polytope depends on the order of the correlators. So this k that you use here, right? The number of measurements, number of outcomes, but it does not depend on the number of parties, right? And this will be reflected later in the method that we give. So this was also inspired on previous. So here some of us we derived some of these Bell inequalities following the polytope approach that I showed previously. That one could simplify it and well guess some classes of inequalities like this one, right? And then a very nice experiment in Basel 2 years after, right? They actually checked that through a Bell correlation witness, and now the state of the 500,000 number of atoms that these inequalities have been tested, right? But now we want to, instead of given the inequality, try to find the maximal violation by changing your state and measurements, right? Just go to a lab, measure something, and see what is the Bell inequality that you are violating. So yeah, as I said, if you solve this polytope, right, it looks like this. So you have one coordinate would be like S0, S1, here maybe S00, and so on, right? And then you solve this, and okay, the resolution is not enough, but you get the idea, right? So you try one by one and say, okay, this works, right? But this is a huge list. And actually, so if you plot a slice of the polytope for different values, right, you observe that it looks a bit like this. So it's very polyhedral for a small number of parties, but if you keep increasing that, then you see that it becomes more and more smooth, right? And also, yeah, I think that if you follow like the list, it's what's the physical significance of each inequality, or if they are all equally relevant, it's kind of a question that you cannot really answer, right? Because I mean, there are so many inequalities that you don't know which are the good ones or not. So here comes the main observation of my talk, right? I think it's just the analogy. So this would be kind of what was if you played video games, Lara Croft in the 80s, right? And then you see that as the system becomes larger, right? So if you make increase the number of parties, right? So what you increase the resolution of the entity that you are trying to describe, right? So over time, so this would mean increasing the number of parties, so you increase the number of facets of this polytope. But you see that you are trying to describe always the same entity, right? So, and why does this happen, right? Because in general, if you have just a full polytope and you increase the number of parties, I mean, it's completely new what you get, right? So here, why does this phenomenon happen? So this is just because, so if we look at what local deterministic strategy, so a vertex of the polytope looks like in this case, so we can picture it like this, right? So we have different players, Alice, Bob, and so on. And each of them would, so you can picture that in a graph because it's symmetric Bell inequality, so everyone is connected with everyone. It's two-body correlators, right? So I represent that with the lines. And then I would represent Alice and Charlie with the same color, meaning that they are using the same local deterministic strategy. And then, well, this is permutational invariant, so it means that only the amount of parties that choose the same color is the relevant parameter here. So this allows you to parameterize the local deterministic strategies in a very efficient way, right? So let's call x0 the number of greens, x1 the number of reds, and so on, right? Of course, they must sum up to n, right? Because these are all the possibilities that you have. So this means that your correlators now gain algebraic structure that we did not use in the case of solving the polytope, right? It was just a random cloud of points that you send to the solver and you get the list of inequalities back. But actually you have relations like this, right? So this is a Hadamard matrix. Well, it's not very important, but the point is that there are some polynomial relations here that are satisfied for every local deterministic strategy. So now when you want to compute the convex hull of this, right, this will look like this. So these x's have to be non-negative integers, so counting the number of greens, rights, and so on in the graph, right? And then you have this vector s that depends on x, that parameterizes your local deterministic strategy, and is subject to these binding equations. So now the goal is that, well, let's define a manifold that interpolates through all these vertices, right? And then we compute the convex hull of this, right? So we are going to relax this problem because in this formulation, this is too hard to solve, or well, we have to resort to the polytope, right? But well, the first relaxation of this problem is actually very easy. So instead of considering these integers, now we just take them as real numbers. So we have really a manifold that interpolates through all the vertices here, right? So the convex hull can only be larger because I'm considering a larger set of points, right? So I'm going to be describing not the polytope, but something that is slightly larger, right? So I'm going to miss some information. So if my point is between the two sets, right, then I will miss it. We'll see that the method, I mean, this is actually very, very little what you miss, right? So now you would have these constraints, right? So the x's have to be still non-negative, right? And then you have some other constraints like this and the ones that I wrote before, right? And then, well, of course, the second problem that you have is that computing the convex hull of a semi-algebraic set like this one, so this second one is a semi-algebraic set, right? It's also NP hard. So this is why I started by non-negative polynomials and sum of squares. So this brings me to the second relaxation, which is, okay, instead of checking if we can a non-negative polynomial modulo f, right? We're going to write a sum of squares modulo f, right? So we are going to look for a polynomial s that has this form, where these are sum of squares polynomials modulo the ideal generated by the f's. And well, now this I have rewritten my program as a semi-definite program, right? And then, well, the SDP would look like this. So now you would go to the lab, you would generate statistical data on what you have measured. So these are these S star, right? So this is not complex conjugation, this is just to denote that these are your correlations. But then you have an associated moment matrix with this, right? And then you will apply the simplification and so on. And then you would have, subject to that, the things that you can observe is actually the data that you have from the lab, right? So this is the constraints that come from the experimental data point. And then for the experts in semi-definite programming, you know that to each of these constraints, you have an associated dual variable, right? So if this program is not feasible, so it means that the point is outside of your approximation, right? The dual constraint associated to every of these guys is going to be the coefficient of the Bell inequality that you are violating. Right? So these are the results. So we have a method that tests all the Bell inequalities of a certain form with a single SDP instance, right? So now if the experimental point is sufficiently non-local, then the SDP via the dual would give you the Bell inequality that you are violating. And well, the SDP itself is a proof of the classical bound of this Bell inequality. So you don't need to solve any polytope. And what I think that it's different from other hierarchies and so on is that here a problem of if we increase the size of the system, is the SDP more costly or not? So it's not, because actually the n is a parameter of your polynomials, so it just goes inside of the terms of the SDP. It does not change the size of the SDP that you have. So in the case of n parties to inputs to outputs, it's a matrix 6 by 6 with 5 blocks, right? So the block given by f and the 4 blocks given by the non-negativity constraints, and you just have n as a parameter there inside. So to see how it works, for n equal 10, this would be a slice of the polytope, and the blue would be the polytope, and the red would be the first level approximation. And then the data that they measured in the experiment. So you see that also with the blue you have the local polytope. The red is the first level approximation, and the experimental point is also a bit quite far apart. So you see that the method becomes better and better as you increase the size of the system. And then, well, to finish some outlook, so of course you can generalize this to more outcomes and higher order correlators. So spin nematic squeezing will be like for spin 1 or like 3 outcomes inequalities, right, where the polytope approach is already impractical. So we could not do, I mean, we tried that before with the polytope, but it was impossible to get some useful classes of inequalities, right? This is ongoing work that we are doing, and well, this is some kind of nice example, but also we have seen that, well, sometimes the approximation has some problems, so maybe one has to go to higher levels of the hierarchy, so use higher degree sum of square representations. And then, of course, you can also consider higher order correlators, so it means that, so this would be for two-body correlators, we had this kind of polynomial constraints, but three-body, you have different kinds of polynomials and so on, and because they are symmetric, well, it's easy to convince oneself that these Young diagrams come kind of naturally, but well, this is ongoing work that we are doing. And then one can also like apply these methods for Bell inequalities, not just for ordinary, let's say, non-locality, but for non-locality depth. So this will be presented next week by Flavio, this method. And here, well, instead of considering parties that act independently, maybe you allow some of them to join and produce a PR box, so to say, right? And then this would give you a measure on the how strong actually is the non-locality in your system. And then, well, also open questions are like when does the method converge, or where does it not converge if you go with to the infinite level of the hierarchy? right? And then also another thing that we are trying is to, if one can make some kind of self-testing statement on spin squeeze states, which are the ones that maximally evaluate these inequalities. With this, I would like to finish. Thank you very much for your attention.
So is there any question for Jordi? Sorry.